All right. So I wanted to finish up this discussion on the Luby transform. This rateless error correcting code, and we'll take maybe a quick look at what's called a Raptor code as well, combination. And then I want to wrap up the transport layer with some sort of weaknesses of TCP that maybe we can address at some point, not during class. And that'll be that for the transport layer. Next time, I think we'll start the discussion of the network layer. Right. So the Luby transform is basically okay. So let's see. Let's back up here a little bit. We had this Reed-Solomon code. That's this whole arithmetic thing to generate any number of combinations from a few packets. We had this parity packet where we're basically taking the XOR of a few packets to generate one extra packet. And it's enough to receive, if you now do k plus 1 packets, you can receive any k packets and be able to reconstruct the original k packets. Right? So in the case of this parity packet idea, we pretty much need to know that, we're only going to lose one packet, right? One packet out of 3 might get lost, one packet out of 6, right? But we need to know what is the loss rate in order for this to be effective, so we can sort of prepare ahead for it. But if we don't know the loss rate, it gets a little harder. It's very easy if you can do acknowledgements. Right? Then we don't need to worry too much about it. But if we don't have the conventional acknowledgements and the receiver doesn't tell us which packets it lost, then what do we send? Right. So we could maybe some clients, let's say it's a broadcast scenario, right? So some clients lose half the packets, others lose 1%. And so now the best we can hope for, of course, is that the one that loses 1% gets the file quickly, and the other ones get it later. We still have to transmit until the one that loses a lot of packets has everything. We can't do anything about that, but at least we can try to make it so that the recipient receives its file quickly. And in the case of sort of the Mars transmission idea, we want to send, we don't know how lossy the link is at the moment. We just want to get the best capacity out of the link that we can. And then at some point, we will get an ACK back from Mars saying something about what progress we made. But at that point, it's sort of too late already. We really should have delivered We would want to deliver as much data as possible to Mars before we got that acknowledgement back. So what do we send when we don't know what the loss rate is? That's the question. And ideally, for k source packets, so a source packet meaning we have the original file. We chop it up into k same size pieces, right? So for k source packets, we want to be able to decode given k code packets, right? So actually, let me make this a little bigger. I generate a continuous stream of code packets, and then be able to decode on the receiver side after you've received any k code packets. Yeah.
Can you differentiate between code packets and source packets?
Yeah. So a source packet is just like this 1500 byte chunk, and a code packet has something in it saying I'm a combination of some packets, and then there's the combination, basically the XOR of a bunch of source packets. But yes, you do need a little header that says what's in here. Right? Yeah.
So since the combination of packets is parity, then do the source packets also have that header that says like I'm the source packet rather than I'm a
Oh, I'm sorry. I maybe I should clarify that source packets are not transmitted. Right? Source packets are kind of given to the sender. The sender makes code packets, which could potentially be just the XOR of one packet, right? But we think of that as a code packet as well. So now the question is, what are these packets that we should be sending? So one potential way, it's code packets look like header with some packet IDs, and then XOR of all those packets together, source packets. Right. So here's one potential code we could send. Just send the source packet. The first code packet is the first source packet. Second code packet is the second source packet. And then when you get to the end of the transmission, end of the source packets, then you start over from the beginning. Right. So now the k+1 code packet is the first source packet. Right. This is a repetition code. Very simple. Unfortunately, it doesn't get anywhere close to this, be able to decode given any k code packets. So for example, if you're really high loss domain here, you might end up just getting the first packet out of every round. Over and over, you keep getting the first packet. So that doesn't ever get you to the final, to the full source. Or you could, maybe a little more realistic, you just get one out of all the packets all the time, but you're very likely to kind of get the same source packet multiple times and miss out on some of them. So it's not really what we want. So what should we do instead? Well, so you could say the code is example code, like send 3 source packets, and then one code like that, right? So now we send every fourth packet is a parity packet. We talked about that before. So now it's actually, we're in much better shape, because as long as we get 3 out of 4 for any chunk of 3, now we'll be able to decode all those 3 source packets, but still not quite right. So here's another idea. Why don't we just XOR all the packets together and send that over and over? What do you think?
You wouldn't be able to decode it if you XOR'd all of them.
No, that's it. Now we're sending the same packet over and over again. There's no information in there really. Or you could take all the packets minus 1 and XOR all those. Now there's at least some more information in there, but it's actually the same thing as sending every packet individual. There's the same benefit to that. So what's the right distribution there? Like, what should we be sending really? There are a few different approaches, but the standard in the Luby transform, there's a math expression for it, so I'll just look it up. Looks like this. Oh. There. Right. So there's a couple things going on. First, we have to decide how many packets to XOR together. Maybe we say just 1. Right? And then, so now we've decided that the degree is 1. Now the question is, which packet should we send? We don't know which packet the receiver has lost. So the best we can do is send a random packet. So if we chose degree 1, we send a random packet. And it's really, this is a fine code. Actually, so you could say, here's another example. keep sending a random source packet. Right? This actually works. If you don't know the loss rate, this works as well as sending all the packets back to back over and over. Right? But it's kind of a dumb idea. Okay, so the alternative is that we randomly also choose the degree. So should we pick a packet that is degree 1 or degree 2 or like all the packets together? You know, it's actually pretty nice to have every now and then a transmission with all the packets XOR together, because if we're missing one packet, we don't know which one, that one's going to get it, right? But if we're missing 2 packets, it doesn't do anything for us. Right? We can't. Yeah. So we need kind of a distribution of it, and this is the degree distribution. So if we let's just take an example. Say we have 4 packets, right? Yeah.
So if we're sending, it's changing like the degree. Are they keeping like all of the parity packets we send?
Yeah. How do we decode it is the question,
Yeah.
right? Yeah. The receiver gets a little complicated, but it's not so bad. It's not like the other one, the algebraic code we were talking about, Reed-Solomon. But basically, anytime you get a new packet that you haven't seen before, you'd have to look at all the other parity packets if you want, see if like this packet is a part of the expression that formed the other packet, and if so, kind of apply it and get a smaller parity packet back. Right? At some point, you keep applying every time you see a new unique packet, a new unique combination of XORed packets, right? You apply that to everything you have sitting around, and you get more and more of these naked packets, naked source packets, which once you have all of the source packets, then you're done. So yeah, you do need, there's some computational complexity involved in doing that continuous, like an unmasking of those XOR packets. It probably isn't worth it if you have a really high bandwidth link with low latency, because then it'll take more time to do the decoding than it takes to do a retransmission. All right, so let's just take an example. If we have 2 packets, we'll want to send one, like every other packet we want to send with a degree 1, right? And every other packet we want to do a combination. Right? So here is, so for k equals 2, this is a degree 2, right? So 1 over 2 is that, and n is also 2. So every other packet, this actually makes sense, right? We don't know which packets we're going to lose. We can't just send an XOR of both packets. So we send one or the other packet every now and then, or every other time we send one of the 2 packets, and every other time we send the XOR of the 2. And now we're very quickly going to be able to kind of resolve both packets. And the same applies as you have as you increase the number of packets. But the general sort of concept is send quite a few of the low degree packets and not many of the high degree packets. That's the sort of where you want to be. Some, but not too many of the high degree packets. Okay, so that's the Luby transform. It is one of the what are they called? Fountain codes. Fountain code is, I think, a name for basically sending a bunch of XORs. Right? And the Luby transform in particular is the one that has this shape of the distribution. I could be wrong, I didn't refresh my memory on that one. Okay, so the Luby transform has this one problem, that it's really easy to get almost all the packets. But then at the very end, so if you're sending 1,000 packets, you know, it's not so, it's quite easy to get to 991 packets. But then you want to hit the last one. You kind of had to get lucky, right? You have to either get lucky that, oh, I picked a low degree one, which includes that packet that I wanted, or I picked a high degree one, which is a low probability event. So it's got to be one of the two. So it's kind of slow at the end, so you end up sending a lot of extra redundant packets at the end. You don't know which ones are redundant, right, as a transmitter. So you just end up sending a lot where a lot of useless stuff. So an alternative to this is called, or sort of an extension of the Luby transform is called a Raptor code. And let's see, Raptor. And it's like rapid, and then there's a turbo code for whatever reason. I forget what the turbo is for. The general idea is it should be quick to decode even at the end, right? You should be able to get all the packets quickly, not just the first 99%. So how do we do that? Well, that's a combination, actually, of known loss rate code, like a Reed-Solomon code, let's say. So we say, oh, I can handle 1% loss rate. So now I code my packets initially so that it's enough that I have any 99% of these packets. So I get sort of make that extra, or if we make it in the case of the XOR parity thing, it's hard to make it perfect there, but as an example, so we have 1,000 packets and 100 packets, and we want to be able to handle like the last one being missing. Well, then we just make sure we send a packet that is the XOR of all of them as well. Right? So now it's enough that we get any 100 packets, including that one XOR packet. It's an internal 1% loss code. The Reed-Solomon code allows you to set any kind of loss rate, and I think they target something more like 5%, let's say. So now, you can handle, as long as you get any 100 packets, 5% packet loss, we can immediately decode. All right, and then we don't actually know the loss rate. So you do first code the source packets with a known rate loss for, and what was it called then? Erasure, yeah. Forward erasure code. Right. So something like that, right? And then code those packets with a Luby transform. So now the Luby transform is really easy, fast to do up to 95% of the packets, and then we kind of start struggling. But using this, and they call this the outer code, and this is the inner code. I think it should be the other way around, but so now we already have 95% of the packets, and now we can deliver that to the outer code, which can get the source packets given any 95% of the, or given any sort of 100 packets, or losing those 5% doesn't hurt it. So that's a Raptor code, and that's actually, those are in active use, and I thought it was in cellular, in broadcast stuff for cellular wireless, and I don't actually know where you use broadcast in those, but that's okay. Let's see, I thought it was an example of a combination. What do we have here? Okay, right. Okay, so here's the gray sequence is another way. Low density parity check is another way to do like a fixed rate loss code, just like the Reed-Solomon code, and then on top of that the Luby transform. Right. Well worth taking another look at if this sounds interesting, or if you're looking to do that bonus thing of the homework. I think it'll be fine to do just the Dooby transform. It'll be complicated enough. But if you want to try to hit this in a Raptor code, is basically with a 99% probability getting in a good Raptor code. With a 99% probability, any K packets will get you the source. Right? So you receive any K packets out of this coded thing, you will get the original source packets with unknown loss rate. That's really a beautiful thing. Okay, so that's all I've got for forward error or erasure codes and error collecting codes. Any more questions on that before we move on to trashing TCP? Okay, so we talked quite a bit about like how TCP works, and TCP is really king on the internet at the moment. It's what everyone uses except for a few things where you maybe don't care so much about losses. In part, it's sort of still in the lead because it's extremely hard to replace, just because there's a whole bunch of machines inside of the internet, inside of the network, that looks at these headers and makes decisions, and if surprising things show up there, protocols they haven't seen, they will basically drop the packets. That's in part it, but it's also in part that we don't really have a much better solution. Like, you could make some incremental changes to improve it, but we don't really have something that really fundamentally improves on TCP. So that said, there's a few weaknesses or missing features that would be really nice to have in TCP, and I think someone's going to have to, at some point, come up with a replacement and fix this. Okay, so let's start with one. And I don't know that this is something we can fix necessarily, but you can actually you can spoof spoofable packets. Spoonable, nice, yeah. Spoofing means like you send a packet that looks like a real packet. It looks like it came from the intended, or from the real sender, but it's actually from you. So an example, I start a bank transfer. Like, you ask me to send you those $5 I owe you, right? And you know that this is my bank, like I bank with Chase, let's say. And so I log into Chase and I say, okay, let's transfer $5 to this guy. And I put all the various important information in there, secrets that only I know, my password and whatever, to make it good. And so let's say it starts out like, yeah, I want to make a transfer. Right? And the bank asks back, how much do you want to transfer? Right? And then I say $5, and then that's it. So now you could imagine this attacker he knows, or that is you know that I'm about to make this transfer with Chase Bank. You know my IP address. You know the bank's port, right? I'm going to talk to port 80 at the bank. You don't necessarily know my source port because you can't look at my traffic. So that makes things a little difficult. And you don't necessarily know the sequence numbers. Right. But let's say for now that you take a reasonable guess. It used to be, at least, that the source port was just incrementing. So whenever you start a new TCP session, you have the next port. It goes up and then it starts from the bottom again, around and around. So now we talk first, and you see the port number, right, in our communication, and then you can pretty much guess what the bank port number is going to be, like for my bank session. So now you could just keep sending a bunch of packets to the bank saying $1 million, right? With the right source number, right? You have a source port. Right? You have some idea what the source port's going to be. So let's just send it for 10 different source ports. Just send a whole bunch of those packets. The bank's not going to do anything about that. They'll just see a bunch of these weird-looking packets and send their RST back, right? Because they don't know anything about this session until my transfer comes in. And if you got it all right, it'll look like that came from me. So now suddenly your $1 million number comes in before my $5 number, and now I've authorized a transfer of $1 million. What makes it hard to spoof these packets? It's the randomness in the source port, and it's the randomness in the initial sequence number. Right? We know that we can easily tell, oh, how many bytes is there in this transfer exchange? So we know how much the sequence number is going to increase, but if the sequence number is if the initial sequence number is random, it's hard for me to guess what it's going to be. So I could try many, right? But it's a range of 4 billion, so that makes it a little difficult. It used to be that they weren't so careful about random number generators, and then you could easily guess what that sequence number is going to be. You just send, say, a couple of hundred different attempts, and you get it. So the only safety is in random ports and initial sequence number. Okay, so I guess generally speaking, anything you send in TCP is plain text, of course. So anyone that is on the path can change the TCP stream to any extent. Right? A man-in-the-middle attacker, like your internet service provider, can do whatever they want with your TCP stream. It used to be popular for a while for ISPs to inject advertisements in web pages. Right? So you would download a Google page, and then right there are some Comcast ads. Right? They stopped doing that, in part because sensible website providers started using HTTPS. With HTTPS, you can't do anything. You can't inject anything there. That's all encrypted. If you try to change the packet will just be rejected because it doesn't fit anymore. Right. So, but not only can you listen to it, and not only can you do whatever you want to it if you are on the path that your packet travels, but you can actually modify the TCP stream from outside by sending these kind of spoof packets. So that's a little unfortunate. It'd be better if there was some cryptography in it to make it impossible to change it. So crypto would have been nice. Right. So for example, one thing you could do is you could accompany each TCP packet with a hash that includes all the contents of the previous TCP packets. A little bit like a blockchain, you know, get on the hype train without any distributed agreement. And then it would be impossible for an attacker to spoof a packet because they haven't seen all the communication that happened before. So that would be sort of one way to address it. Okay, what else is wrong with TCP? Oh yeah, another way to address it is to require all TCP connections to be encrypted, of course. That's SSL. Right? And secure sockets, or there's some other names for it now. I forget. There's all sorts of different ways to do encrypted TCP connections. Maybe it's right to put that on top of TCP, right? Or maybe it should be part of TCP. I think integrity should have been part of TCP, but probably not secrecy. Okay. Another thing is there's no fairness guarantee, right? So TCP has this sort of cooperative notion of fairness. You are supposed to follow like the additive increase, slow increase, multiplicative decrease, go down by half. In fact, it's more than that. Whenever you go down by half, you set the the target congestion window to half, but you actually drop to 0 and then do a slow startup. I suggest you take a look in the textbook to see the exact details of it. It's not that important, but in any case, this is just sort of a guideline. Like if you want to be a TCP implementation, this is what you do. You increment slowly and you drop quickly. Rogue TCP implementations can do whatever they want. And moreover, start more than one, get more than your share, right? So if you want to download something quickly, just start one stream downloading the first half and another stream downloading the second half, and now you get twice as much bandwidth as your neighbor. And that doesn't seem quite right. I list this as a TCP weakness. It really is a weakness of the end-to-end principle, right? If the network doesn't care about fairness at all they do is take the first packet that came in, put it out on the next link. Then you're not going to get anything better than that. But it seems like that sort of thing ought to be fixed. Maybe it means we have to change the network. It certainly wouldn't be enough to just change TCP, because you could still have other people not use whatever you come up with. Okay, another one, it's incompatible with lossy links. So what do I mean by that? Well, congestion control in TCP is based on packet losses, right? So we're using a packet loss to indicate the network is full. But what if we lost a packet not because the network is full, but because a link is lossy? Now we're still going to reduce our rate. That doesn't make any sense. If you lost a packet because a bird came in front of the antenna for a moment, right? Or in front of your laser link, let's say, then it doesn't make any sense to reduce your rate. You should continue at the full rate or maybe go even faster to make up for that loss. But TCP will quickly reduce the rate because it thinks that some buffer got full along the way in some router. Right? So it interprets any packet loss as a congestion-related loss. And I think that's fine as long as you are using links that aren't lossy. Right? If you're using optical fibers, if you're using like a normal Ethernet cable and you don't have a lot of other electronics nearby, that's fine. But if you're using something that's a little more loss prone, like a wireless link, it's going to be a real problem. Fortunately, you could put in, and at least with Wi-Fi, there's loss management on the link itself. So it does retransmission locally for the link. So TCP doesn't see that loss because it kind of recovers locally. But yeah, generally speaking, I think it'd be much better if TCP got a signal about a lost packet, like why it was lost. One way or another, we shouldn't just have should be two signals. One is the link is getting lossy, the other one, or the path is getting lost, and the other one is the path is getting congested. There is some work on this. It's called ECN, Early Congestion Notification. There's a bit in the TCP header that a router can set along the way. If it says, like, if it thinks that, oh, this queue is getting too full, it's not quite full yet, but it's really getting too full, then it can start setting bits, these ECN bits, to say, I would have dropped this packet. And it doesn't, but it could have. And then the endpoint, when it acknowledges the packet, it'll forward that ECN bit and say, this packet, it could have gotten dropped. So now that the sender could reduce its rate without having lost a packet. So now we have a congestion notification that is sort of separate from loss notification. You could argue whether we should interpret losses as congestion at all, and at the moment we have no choice. We have to do that. Okay, and then there's poor performance on high bandwidth delay links. So we have the congestion control mechanism. It starts with a really small congestion window, and then it increases it based on like the number of round trips. So if we ignore slow start for now, and even slow start is kind of slow. I mean, it's called slow start, but it's actually exponential, right? But it still takes quite a while. If we ignore that part, we just say we are at some steady state. We have a loss. Now we drop it to half, and then it takes forever until we get back to a reasonable rate. What do I mean by that? Well, so we have say we're doing a link to, well, let's do the Mars example. So we have a really high bandwidth, like a big antenna, right? We can do a nice bandwidth link to Mars. But the round trip time is 8 minutes when we're lucky and 30 minutes when it's bad. And so now it's going to take us 8 minutes before we get to send one more packet in this congestion window. Right? And we could be sending a gigabit a second through this big fat antenna, but in fact we're sending like 15 packets, and then 8 minutes later we're sending 16 packets. Right? That really isn't right. So rate control is based on round trip time, right? Or is kind of slowed down by long RTT. It would be better if we can get an estimate of the link capacity after one round trip time. All right, so now we say, okay, it's probably something like a half a gigabit per second, and then we go at half a gigabit, and then next round trip time we see, oh, it actually was a little more, so then we can bump it up a little more. Right? That would be nice. Not this adjust like by such a minimum amount every round trip time. So this is only important on high bandwidth, like bandwidth delay is like bandwidth times delay links, right? That is really the sort of the volume of that long pipe. It's a fat pipe, and it's really long going to the other end. If it's a fat pipe that's really short, the bandwidth delay product, like the volume of that pipe, isn't much. That's the number of packets you can put in the congestion window. It's really not a whole lot, so that's fine. But for this big, fat, long pipe, you should fill it. Like your congestion window should be the same size at that whole volume of the pipe. But we just never get there because of this slow adaptation. Right, did I have any other? Oh yeah, okay. I have a couple more. So it supports only one network interface. Okay, so maybe this, somehow you're used to this, or maybe you never noticed, but we make a connection, we SSH to some server, and the session is based on the IP address and ports, right? So if I connect my computer or my phone or whatever it is to the internet with more than one connection, the TCP will pick one. Like the operating system will somehow arbitrarily decide that, the wired internet is better than the Wi-Fi, so I'm going to go with wired first. If wired is available, we'll just use that. And the TCP connection will just go over that link. It'd be much better if it went over both. Right? It'd be twice as fast, or maybe more. Or if we have high losses on one, maybe we have low losses on the other. Like there's a lot you could do if you could kind of combine these. Say the Wi-Fi is really lossy, but it's really fast. And then we have this slow old cable, like DSL thing, and it doesn't have any losses, but it's really slow. Right? We could combine those two and make a beautiful transport protocol. But yeah, TCP doesn't really doesn't really like that. Sessions are based on one pair of port IP, right? That's it. So no way to multiplex sessions over many interfaces, right? And moreover, there's no way to kind of handle when one interface goes down either. So I have my Wi-Fi, right? Say they always decided Wi-Fi is best. So I'm using that, and then the Wi-Fi goes down for whatever reason. Someone starts the microwave oven, let's say, and now I only have a TCP connection going. An Ethernet connection left. It's kind of slower, but really my TCP connection should be going over that one. But it doesn't work either. There's just, because the TCP session is based on the IP address, there's one IP address per network interface. It's not per machine, it's per network interface. So no failover between network interfaces. And along similar lines, there's also no mobility. I don't know if you ever try, you're here and you SSH to some server, and then you close your laptop, you go home, you open it up, and now the socket is, what do I say? Well, there's some error message. I forget the name of the error message, but basically the connection is broken, right? Why is that? It doesn't make any sense. I am still logged into this. Why am I not logged into this machine? Just because I went from here to home? That's kind of stupid. So you can solve this at the application layer. Right? You can build a new SSH that notices when a connection breaks and then logs back in, and on the receiver side preserves existing sessions and try to match up, because usually, at least if you're me, you have like 15 ongoing SSH connections into the same machine, and try to match that up, and that would probably work. But now that's application level stuff, so now it still wouldn't work on your other programs. Right? You'd have to fix every program. So a good transportation transport layer really should support many interfaces, should support mobility, should support failover seamlessly, and it should work for every program. Okay, I think that's all I've got about TCP weaknesses. Yeah?
Thinking that most of these aren't part of TCP, but the end-to-end principle. For many of those to work, the network has to provide some kind of feedback.
Okay. Interesting. That's a interesting point of view. I think it's true for this one for sure. This one, maybe. Not obvious. Right. There's other ways that we can measure congestion. Like the round trip time depends on queue length. So you ought to be able to detect congestion by saying, oh, it's much longer than it used to be. Right? There's a signal there, so it's not clear that it has to be violating end-to-end principle. And you could imagine that we could make changes to the network, but they don't have to be protocol dependent. Like you could say, oh, if I lose a packet, you have to send a notification back. That sounds relatively expensive to send all those packets. There's probably things we can do that sort of improve the network layer without making it aware of applications or other transport layers above. So, but I totally agree that without changing the network, you're going to have a harder time. And people have spent a lot of time trying to figure out how to stop doing this. Okay, let's see about the other ones. Right, so I think here you're probably entirely wrong. I think that you can estimate the bandwidth by sending a few packets and then just see kind of how much they got spread out in time, sort of thing. I don't think you need any support from the network. see what else. And then for this one, this does, yeah, if you want to support mobility, you could imagine doing that at the network layer. You say this address leads to my computer no matter where the computer is. That would be really nice. We'll talk about this in the network layer discussion. But you can also do it at the transport layer. Like the transport layer could be persistent, and it notices, oh, I lost the previous connection, but I remember what it used to be, and both endpoints remember this, and you could be able to restore it. Right. So there's one protocol called SCTP, Stream Control Transport Protocol, something like that. And that one does support these, all of these three, I believe. There was a kind of a popular movement when I was doing my PhD, say 15 years ago or so, but it didn't really make it. And the problem is, I think for that one, the main problem was that all of the NAT gateways out there, they were keeping translation tables, right, with TCP port, TCP source address port sort of things. And now comes this SCTP protocol with the ports somewhere else, and I've never heard of SCTP. What am I supposed to do with this? Drop it on the ground. So now you couldn't use SCTP for anything that's behind a NAT gateway, and that was kind of the death of that. Maybe we can come up with something that is TCP compatible, or maybe we can, I'm not sure. But it feels like something ought to get fixed, and one of you ought to do it. All right. Did I promise anything else for today? No, I think that's about it. So, yeah, next time we're moving down to the network layer. So the network layer is basically how do we get from one IP address to another IP address in this enormous and really diverse network without wasting too much memory on the various routers and too much bandwidth on the various links. And we'll spend several weeks on that, I think. Yeah. What the midterm? Let's see. Wasn't it the 18th? 18th. Yeah.
Would you suggest us for the homework to use Raptor codes, or should we use?
I would start with a Luby, right? And then if you want to make it even faster, then add an outer code, right, with a fixed loss. But the Luby thing it's going to be really cool on its own. So
Luby will be mainly for the extra bonus, right?
yeah, exactly.
Okay.
Right. Yeah, definitely do the other things first. All right. Thanks a lot. See you on Friday.